In the name of Almighty God, I am Master Hassan Kashi, and today I want to talk about direct current glow discharge. Direct current glow discharge in the low pressure regime have long been used for gas lasers and fluorescent lamps. DC discharge are attractive to study because the solution is time independent. The first dimension and two dimensions models show how to use the DC discharge interface to set up an analysis of a positive column. The discharge is sustained by emission of secondary electrons at the cathode. A DC glow discharge is a low pressure, self sustained electric discharge in a weakly ionized gas between two electrodes, producing a non thermal plasma. It happens when a high DC voltage is applied, accelerating electrons from the cathode that collide with gas atoms, creating ions and more electrons in an avalanche like process. This process results in a luminous, non-equilibrium plasma used for applications such as surface treatment for microscopy grids and sputtering in vacuum coating processes. And how it works. The first one is gas breakdown. A DC voltage is applied across two electrodes, a cathode and an anode, separated by a gas at low pressure. The next one is electron acceleration. Electrons are emitted from the cathode and accelerated by the electric field towards the anode. And what is about collisions and ionization? As these electrons travels, they collide with neutral gas atoms and molecules, transferring energy and causing ionization and excitation. And the next one is secondary emission. Some of these energetic electrons knock out other electrons from atoms, a secondary electron emission, creating more charge carriers. The next one is plasma formation. The continuous process of ionization and excitation maintains a steady self-sustained discharge, creating a luminous non-thermal plasma. And what about key characteristics? The first one is non-thermal plasma. The plasma generated is not in thermal equilibrium, meaning electrons have much higher energy and thus temperature than the heavier ions and neutral particles. The next one is luminous emission. The glow is a result of excited atoms and metastable species releasing energy as they relax. The next one is field electrodes. A DC glow discharge involves a fixed cathode and anode. And what about applications? Surface treatment is the first application and used to alter welting properties and clean surface, such as thin grids for microscopy, ensuring uniform sample adhesion. The next one is vacuum coating, serves as a source of high energy ions for sputtering and ion plating processes, which are used to deposit thin films. The next one is analytical techniques. Glow discharge is used in spectrochemical analysis like GD, OES, and GDMS for direct elemental analysis of solid samples. A glow discharge is a plasma formed by the passage of electric current through a gas. It is often created by applying a voltage between two electrodes in a gas tube containing a low pressure gas. When the voltage exceeds a value called the striking voltage, the gas ionization becomes self sustaining and the tube glows with a colored light. The color depends on the gas used. Glow discharges are used as a source of light in devices such as neon lights, cold cathode fluorescent lamps, and plasma screen televisions. Analyzing the light produced with spectroscopy can reveal information about the atomic interactions in the gas. So, glow discharges are used in plasma physics and analytical chemistry. They are also used in the surface treatment technique called sputtering. And what is about electrical conduction in gas? Voltage current characteristics of electrical discharge in neon and one tour with two planar electrodes separated by 50 centimeters. A. Random pulses by cosmic radiation. B. Saturation current. C. Avalanche. Townsend discharge. D. Self-sustained Townsend discharge. E. Unstable region corona discharge. F. Subnormal glue discharge. G. Normal glue discharge. H. Abnormal glue discharge. I. Unstable region glue arc transition. J and K. Electric arc. A to D region is dark discharge. Ionization happens. Current below 10 microamps. F to H region glow discharge. The plasma emits a faint glow. I to K region arc discharge. Large amounts of radiation produce. Conduction in a gas requires charge carriers, which can be either electrons or ions. Charge carriers come from ionizing some of the gas molecules. In terms of current flow, glue discharge falls between dark discharge and arc discharge. In a dark discharge, the gas is ionized. The carriers are generated by a radiation source such as ultraviolet light or cosmic rays. At higher voltage, across the anode and cathode, the freed carriers can gain enough energy so that additional carriers are freed during collisions. The process is Townsend avalanche or multiplication. In a glow discharge, the carrier generation process reaches a point where the average electron leaving the cathode allows another electron to leave the cathode. For example, the average electron may cause dozens of ionizing collisions via the Townsend avalanche. The resulting positive ions head toward the cathode, and a fraction of those that cause collisions with the cathode will dislodge an electron by secondary emission. In an arc discharge, electrons leave the cathode by thermionic emission and field emission, and the gas is ionized by thermal means. Below the breakdown voltage, there is a little to no glow, and the electric field is uniform. When the electric field increases enough to cause ionization, the Townsend discharge starts. When a glow discharge develops, the electric field is considerably modified by the presence of positive ions. The field is concentrated near the cathode. The glow discharge starts as a normal glow. As the current is increased, more of the cathode surface is involved in the glow. When the current is increased above the level where the entire cathode surface is involved, the discharge is known as abnormal glow. If the current is increased still further, other factors come into play and an arc discharge begins. And what about the mechanism? The simplest type of glue discharge is a direct current glue discharge in its simplest form. It consists of two electrodes in a cell held at low pressure zero point 0.1 to 10 torr, about 1 divided into 10,000 to 1 divided by 100 at atmospheric pressure. A low pressure is used to increase the mean free path for a fixed electrical field. A longer mean free path allows a charged particle to gain more energy before colliding with another particle. The cell is typically filled with neon, but other gases can also be used. An electric potential of several hundred volts is applied between the two electrodes. A small fraction of the population of atoms within the cell is initially ionized through random processes, such as thermal collisions between atoms or by gamma rays. The positive ions are driven towards the cathode by the electric potential, and the electrons are driven towards the anode by the same potential. The initial population of ions and electrons collides with other atoms, exciting or ionizing them. As long as the potential is maintained, a population of ions and electrons remains. The second, and what about the secondary emission? Some of the ion's kinetic energy is transferred to the cathode. This happens partially through the ions striking the cathode directly. The primary mechanism, however, is less direct. Ion strikes the more numerous neutral gas atom, transferring a portion of their energy to them. These neutral atoms then strike the cathode. Whichever species ions or atoms strike the cathode, collisions within the cathode redistribute this energy, resulting in electrons ejected from the cathode. This process is known as secondary electron emission. Once free of the cathode, the electric field accelerates electrons into the bulk of the glow discharge. Atoms can then be excited by collision with ions, electrons, or other atoms that have been previously excited by collisions. And what is about light production? Once excited, atoms will lose their energy fairly quickly. Of the various ways that this energy can be lost, the most important is radiatively, meaning that a photon is released to carry the energy away. In optical atomic spectroscopy, the wavelength of this photon can be used to determine the identity of the atom, that is which chemical element it is, and the number of the photon is directly proportional to the concentration of that element in that sample. Some collisions, those of high enough energy, will cause ionization. In atomic mass spectrometry, these ions are detected. Their mass identifies the types of atoms, and their quantity reveals the amount of that element in the sample. The illustration to the right shows the main regions that may be present in a glow discharge. Regions described as glows emit significant light. Regions labeled as dark space don't. As the discharge becomes more extended, for example, stretched horizontally in the geometry of the illustrations, the positive column may become straightened, that is, alternating dark and bright region may form. Compressing the discharge horizontally will result in fewer regions. The positive column will be compressed while the negative glow will remain the same size. And with small enough gaps, the positive column will disappear altogether. In an analytical glow discharge, the discharge is primarily a negative glow with dark region above and below it. And what is about the cathode layer? The cathode layer begins with the actin dark space and ends with the negative glue region. The cathode layers shorten with increased gas pressure. The cathode layer has a positive space charge and a strong electric field. And what is about a strong actin dark space? Electrons leave the cathode with an energy of about 1 electron volt, which is not enough to ionize or excite atoms, leaving a thin dark layer next to the cathode. And what is about cathode glue? Electrons from the cathode eventually attain enough energy to excite atoms. These excited atoms quickly fall back to the ground state, emitting light at a wavelength corresponding to the difference between the energy bands of the atoms. This gallows is seen very near the cathode. What is about the cathode space? As electrons from the cathode gain more energy, they tend to ionize rather than excite atoms. Excited atoms quickly fall back to ground level, emitting light. However, when atoms are ionized, the opposite charge are separated and don't immediately recombine. This results in more ions and electrons but no lights. This region is sometimes called Crookes dark space and sometimes referred to as cathode fall because the large voltage drop in the tube happens in this region. And what is about negative glow? The ionization in the cathode dark space results in a high electron density but slower electrons, making it easier for the electrons to recombine with positive ions, leading to intense light through a process called Beamstrahlung radiation. What is about Faraday dark space? As the electrons keep losing energy, less light is emitted, resulting in another space, dark. And what is about an anode layer? The anode layer begins with the positive column and ends at the anode. The anode layer has a negative space charge and a moderate electric field. And what is about positive column? With fewer ions, the electric field increases, resulting in electrons with the energy of about 2 electron volts, which is enough to excite atoms and produce light. With a longer glow discharge tube, the longer space is occupied by a longer positive column, while the cathode layer remains the same. For example, with a neon sign, the positive columns occupies almost the entire length of the tube. And what is about anode glow? An electric field increases results in the anode glow. And what is about anode dark space? Fewer electrons results in another dark space. And what is about striations? Bands of alternating light and dark in the positive column are called striations. There is no universal mechanism explaining the striations for all conditions of gas and pressure producing them, but recent theoretical and modeling studies supported with the experimental results mention the importance of the Dufour effect. And what is about the context of sputtering? Main simulation sputtering, in addition to causing secondary emission, positive ions can strike the cathode with sufficient force to eject particles of the material from which the cathode is made. This process is called sputtering and is gradually ablates the cathode. Sputtering is useful when using a spectroscopy to analyze the composition of the cathode, as is done in glow discharge optical emission spectroscopy. However, sputtering is not desirable when glow discharge is used for lighting, because it shortens the life of the lamps. For example, neon signs have hollow cathodes designed to minimize sputtering and contain charcoal to continuously remove undesired ions and atoms. And what is about carrier gas? In the context of sputtering, the gas in the tube is called carrier gas because it carries the particle from the cathode. And what is about the color difference? Because of the sputtering occurring at the cathode, the colors emitted from the region near the cathode are quite different from the anode. Particles sputtered from the cathode are excited and emit radiations from the metal and oxides that make up the cathode. The radiation from these particles combines with radiation from excited carrier gas, giving the cathode region a white or blue color, while in the rest of the tube, radiation is only from the carrier gas and tends to be more monochromatic. Electrons near the cathode are less energetic than the rest of the tube. Surrounding the cathode is a negative field, which slows electrons as they are ejected from the surface. Only those electrons with the highest velocity are able to escape this field, and those without enough kinetic energy are pulled back into the cathode. Once outside the negative field, the attraction from the positive field begins to accelerate these electrons toward the anode. During this acceleration, electrons are deflected and slowed down by positive ions speeding toward the cathode, which in turn produces bright blue-white Bremsstrahlung radiation in the negative glow region. And what is about using analytical chemistry? Glow discharge can be used to analyze the elemental and sometimes molecular composition of solids, liquids, and gases, but elemental analysis of solids is the most common. In this arrangement, the sample is used as the cathode. As mentioned earlier, gas ions and atoms striking the sample surface knock atoms off of it, a process known as sputtering. The spotted atom, now in the gas phase, can be detected by atomic absorption, but this is a comparatively rare strategy. Instead, atomic emission and mass spectrometry are usually used. Collisions between the gas phase sample atoms and the plasma gas pass energy to the sample atoms. This energy can excite the atoms, after which they can lose their energy through atomic emission. By observing the wavelength of the emitted light, the atom's identity can be determined. By observing the intensity of the emission, the concentration of atoms of that type can be determined. Energy gained through collisions can also ionize the sample atoms. The ions can then be detected by mass spectrometry. In this case, it is the mass of the ion that identifies the element and the number of ions that reflects the concentration. This method is referred to as glow discharge mass spectrometry or GDMS, and it has detection limits down to the sub-ppb range for most elements that are nearly matrix independent. Depth analysis. Both bulk and depth analysis of solids may be performed with glow discharge. Bulk analysis assumes that the sample is fairly homogeneous and averages the emission of or most spectrometric signal over time. Depth analysis relies on tracking the signal in time, therefore is the same as tracking the elemental composition in depth. Depth analysis requires greater control over operational parameters. For example, conditions, current, potential, pressure need to be adjusted so that the crater produced by a sputtering is flat bottom. That is, so that the depth analyzed over the crater area is uniform. In bulk measurement, a rough or rounded crater bottom would not adversely impact analysis. Under the best conditions, depth resolution in the single nanometer range has been achieved. In fact, within molecule resolution has been demonstrated. The chemistry of ions and neutral in vacuum is called gas phase ion chemistry and is part of the analytical study that includes gas discharge. And what is about powering modes? DC powered neon lamp showing glow discharge surrounding only the cathode. In analytical chemistry, glow discharge are usually operated in direct current mode. For direct current, the cathode, which is the sample in solid analysis, must be conductive. In contrast, analysis of non-conductive cathode requires the use of high-frequency alternating current. The potential, pressure, and the current are interrelated. Only two can be directly controlled at once, while the third must be allowed to vary. The pressure is most typically held constant, but other schemes may be used. The pressure and current may be held constant while potential is allowed to vary. The pressure and voltage may be held constant but the current is allowed to vary. The power, which is the product of voltage and current, may be held constant while the pressure is allowed to vary. Glow discharge may also be operated in radio frequency. The use of this radio frequency will establish a negative DC bias voltage on the sample surface. The DC bias is the result of an alternating current waveform that is centered about negative potential. As such, it more or less represents the average potential residing on the sample surface. Radio frequency has ability to appear to follow through insulators and non-conductive materials. So both radio frequency and direct current glow discharge can be operated in pulsed mode, where the potential is turned on and off. This allows higher instantaneous powers to be applied without excessively heating the cathode. This higher instantaneous power produces higher instantaneous signals aiding detection. Combining time resolved detection with pulse powering result in additional benefits. In atomic emission, analytic atoms emit during different portions of the pulse than background atoms, allowing the two to be discriminated. Analogously, in mass spectrometry, sample and background ions are created at different times. And what is about application to analog of computing? An interesting application for using glue discharge was described in a 2002 scientific paper by Renz and Hanem and other researchers, according to a Nature News article describing the work. Researchers at Imperial College London demonstrated how they built a mini map that glues along the shortest route between 2 points. The Nature News article describes the system as follows. To make the 1 inch London cheap, the team etched a plan of the city centre on a glass slide, fitting a flat lid over the top, turned the streets into hollow connected tubes. They filled these with helium gas and inserted electrodes at key tourist hubs. When a voltage is applied between 2 points, electricity naturally runs through the streets along the shortest route from A to B, and the gas glows like a tiny neon strip light. The approach itself provides a novel visible and analog computing approach for solving a wide class of maze searching problems based on the properties of lightening up of a glow discharge in microfluid chips. And what is about application to voltage regulation? A voltage regulator tube in operation in the mid 20th century prior to the development of solid-state components such as Zener diodes. Voltage regulation in circuit was often accomplished within voltage regulator tubes which used glow discharge. And what about plasma-enabled synthesis and modification of advanced materials for electrochemical energy storage, discharge processes, and modes of non-thermal plasma discharge processes? Glow discharge is a widely used way to produce non-thermal plasma, which owes its name to the fact that plasma is luminous. According to more descriptive physical definition, a glow discharge is the self-sustained continuous directly current or DC discharge having a cold cathode that emits electrons as a result of secondary emission mostly induced by positive ions. This simulation displays the schematic diagram of discharge processes in a low current, high voltage device where the gas is weakly ionized. When a high potential is applied to two electrodes, discharge or ionization initiates with the electron atoms collision in gas, which results in the emission of electrons. The ions electron impact ionization, and the metastable atoms with superscript electron impact excitation. Meanwhile, the metastable atoms, which have more energy than their ground states, can produce cumulative ionization to increase the electron density through penning ionization and metastable ionization and more metastable atoms. Ion impact excitation and the relaxation of metastable atoms generates luminous glow due to the emission of photons with energy and hence wavelength determined by the atomic structure. Besides this process, the dissociation of molecules and charged electrons transfer also take place in plasma. In turns, although there is a continuous loss of electrons at the electrodes, there must be an equal degree of ionization going on by ionization, excitation, and dissociation to maintain the steady state, and the additional electrons can be produced by secondary emission from the cathode, which is also important to maintain a sustainable discharge. To be noted, the discharge processes are strongly influenced by the operating parameter, for example, power, gas, pressure, and electrogeometry. What is about plasma assisted polymer modifications? Plasma sources. The desired plasma surface modification of polymers, which depends on the purpose of application, is obtained using different discharge of plasma. Cold plasma used for polymer surface modification is generally obtained by certain types of gas discharge at low pressure. Glow discharge is a type of plasma that is generated when DC voltage is applied to the electrodes inside a gas tube containing precursor gas in the pressure range of zero point 0.1 to 10 torr. The type of plasma gas used and the process pressure to be maintained determines the minimum voltage required to maintain the discharge. There are different types of glue discharge, such as hollow cathode discharge, penning glow discharge, and magnetron discharge used for deposition. Color discharge has potential application in surface modification of polymers. Atmospheric pressure glow discharge of pure nitrogen, nitrogen hydrogen, or nitrogen ammonia mixtures for surface modification of polyethylene and polypropylene were reported to increase their surface energy with only 10% hydrophobic recovery. Reported increased wettability of various polymers such as low-density polyethylene, polypropylene, polyethylene tetraphthalate, and polytetrafluoroethylene, and textile dynamo Sp21 and dynamo Sp51 by atmospheric pressure. Argon glow discharge, high frequency discharge, or radio frequency discharge are widely applied for surface modification and film formation due to the large volume of stable plasma. High frequency discharge operated at a frequency less than 300 kHz is supplied to the load by means of an external electrode, which reduces the effect of the electrodes and is called less discharge. Depending on the type of the coupling of the electrode to the load, it may be classified as the first one inductively coupled plasma or the second one capacitively coupled plasma. Radio frequency discharge are generally operated at a frequency of 13.56 MHz allowed by the International Communication Authority. Plasma characteristics such as density and composition influence the characteristics of the film deposit. Non-thermal radiofrequency discharge is subdivided into two types, namely low pressure discharge and moderate pressure discharge. Electron relaxation length in low pressure discharge is comparable with discharge size, unlike other under moderate pressure where it is much smaller. Electron energy distribution function is determined by the electric field distribution in the entire region in the low pressure discharge. In moderate pressure discharge, it is determined by the local electric field. Modification of surface physical and chemical properties without affecting bulk properties through radiofrequency plasma modification is advantageous for the design, development, and manufacture of biocompatible polymers. The radiofrequency plasma surface modification of polymers biomedical application has been the topic of extensive investigations pertaining to a wide range of applications. Radiofrequency nitrogen plasma modification of polypropylene investigated at different process conditions for enhancement of bio and blood compatibility was found to be effective in bringing about significant change in the surface properties, including surface chemistry and surface morphology. Thank you so much for watching my video until the end. And here you can see my capsule simulation as a direct current glue discharge, and you see that I have used plasma as a physical module, and I have used several formula and different species for positive and negative argons, and plasma model and for insulation, axial symmetry, ground and metal conduct, and also for dielectric contact. And after the time dependent study, we can see that the result is electron density. Here you can see that the electron density based on 1 per cubic meter, The next one is electron temperature, electron potential, potential on axis, electron temperature on axis, electron density on axis, and excited argon number density on axis, and argon ion number density on axis plot.